it's very dear to me, especially because not just because I specialize in it, but it's a highly, I think, versatile analytical technique which we will touch upon. We'll try and cover as much as possible in the limited time that we have. But of course, we would be more than happy to get more questions from you to make it more as much interactive as possible. So with that, I'm going to start sharing my screen. Yes. I hope my screen is visible to everyone.
Yes, it's visible.
It is visible.
Yeah.
Yes,
Okay.
ma'am.
Yeah. So let's start with the topic. Now, elemental analysis. See, elements are present everywhere. So right from the food we eat, right to the medications that we take, environmental pollution monitoring, or it could be geological samples, everything. So elements are the building blocks of each matter. And hence, elemental analysis is of prime importance because they give us like a chemical fingerprint to understand the basics of a particular sample. So all of us know that the periodic table, which keeps on every year, every few years, there is an element added in the periodic table. So the challenge on an analytical chemist is to keep up with the developments that have been happening in the periodic table discovery, to translate them into a technique which will be able to accurately monitor, analyze, as well as report these particular elements. So out of the 118 elements in the periodic table, there are techniques which can measure almost all of them. Different techniques that can measure different elements. Of course, there are a few like very highly reactive substances, or radioactive substances, or they could be noble gases, which have certain limitations, which have some certain limitations in terms of handling as well as in terms of measurement. So there are specific classified equipments which are used to analyze such kinds of substances, not the ones which we will be currently in this session addressing. So coming to importance of why elemental analysis is highlighted and is continuously getting a few or the other very important news now and then, is primarily because of certain you must have heard of certain cases where the European Union had rejected or flagged off certain Indian food spices. Okay, in the past there were certain concerns about inclusion of heavy metals in certain spices. So the EU banned all spices that coming from India. And later it was found that they did contain a little higher concentration. They were contaminated rather with higher concentration of heavy metals. So it's not just about Indian food products being contaminated, but this is a global scenario. The latest case that I can highlight here is the Maggi noodle case, which happened in 2015, where consumers FSSAI found out that the Maggi noodles, when tested, contained really high concentrations of lead in it. And they had to recall. So Nestle had to recall almost 400 million packets of Maggi from the Indian market. So this is a global challenge that everybody is facing. How to, address how and with the sensitivity levels of each technique going lower each day, it is now possible to determine really trace amounts of elements in different variety of matrices, not just food, not just medications, but the range is very broad, which we'll be discussing in the application session. So what is elemental analysis? See, elemental analysis, this is a fundamental method which is used to determine elemental composition of a sample. So not just elemental composition. So the technique not just tells us about which elements are present, but it can also do quantitative analysis. It can tell us how much of that element is present in the sample, in addition to um, determining isotopic ratios of that particular element. So there are specific techniques which can address that particular application too, like ICP-MS or IRMS. So broadly, elemental analysis can be classified into two categories. We have the conventional or the classical methods, which we can call them also as wet chemistry, where we have two broad subclassifications like gravimetric analysis and volumetric analysis. Gravimetric analysis is based on measuring mass changes, by subjecting the sample to controlled chemical reactions. Well, whereas in volumetric analysis, it involves measuring volumes of a solution that are needed to complete a particular reaction. So volumetric analysis is basically titrimetric methods that we know of, like acid-base titration, precipitation titrations, and so on. And gravimetric analysis will be precipitation, but analyzing the mass after the precipitation has occurred. So for example, if we want to determine sulfate concentration in a sample. So to do that, gravimetric analysis is the most popular, and in fact, it is even accepted by most of the regulatory bodies. So barium chloride is added to the solution. A precipitate is formed of barium sulfate, which is then dried and weighed, which will correlate, and calculations are done post the experimental part to determine the concentration of that sulfate present in the sample. This is gravimetric. In volumetric, we have so many others. So volumetric analysis, titrimetric, if you are aware of, we can have acid-base titrations, complexometric, redox, and so on. So in volumetric analysis, although classical methods, have been here since ages ago, and they are supposedly not that accurate. But in fact, contrary to the belief, regulatory bodies even now do recognize certain volumetric methods, and in fact prefer them sometimes over instrumental techniques when the concentration of that particular element is very high, because volumetric analysis is quick and it is inexpensive. So it can be routinely applied for bulk analysis. Of course, there are also drawbacks to classical methods, like it is very labor intensive, it takes time, and especially for determination of trace elements, it is a challenge because the detection limits are not that low. So with advances happening, what we will cover in this section is the instrumental techniques. The instrumental techniques for elemental analysis can be broadly categorized into spectroscopic, mass-related, X-ray techniques, and CHNS. So let's take the first one, spectroscopic analytical methods. So in AAS, AAS by far is the most popular and the most old instrumental analytical technique available for elemental analysis. The principle is very simple. Okay, it relies on the concept of absorption. So in AAS, a solution containing the analyte is introduced into the flame, which then converts the sample into free ground state atoms, which undergo excitation. So a lamp is used for providing the energy required for the samples to get excited. Once that molecule heats up, it causes the atoms to freely dissociate. The amount of energy that is required for the electrons to move between different energy levels, usually corresponds to specific wavelength of light. So for example, this is the case that I have shown here for lead. So for lead, when a sample containing, if you want to determine concentration of lead in the sample, we subject it to AS, what will happen? The solution will come in contact with the flame. The flame will provide energy required to strip off the solution and form elements or ionize the solution, as we call it. So the electrons will jump from the ground state to the excited state. So in this case, especially for in the case of lead, let's say the energy required to move the electrons from ground state to the first level is 283 nanometers. This is the wavelength that is required. A higher energy will be required for the ground state electron to jump to the higher orbital state, and so on. So for a particular element, there are different wavelengths that are possible to be determined. So that we can determine one element using different wavelengths. However, the wavelength of interest in AAS usually is the one is the E1 level, the one from ground state to the first energy state. This is the most, this energy level is the most intense, and therefore can be used to determine trace elements very easily. Now coming to the instrumental section, the instrument is very simple. So we have a light source, usually a hollow cathode lamp is used. This is the most popular one. An atomizer, okay, which provides energy, a monochromator, a detector, and a signal processor. So a light source, a hollow cathode lamp, which is most popularly used in AES, is made up of the same element. So the cathode of this hollow cathode lamp should be made up of the same element that we want to analyze. Okay. So if I want to analyze lithium, the hollow cathode lamp should be made up of lithium. If I want to analyze arsenic, it should be made up of arsenic, and so on. So for each element in AAS, there is a different light source that has to be replaced each time. Then there is a chopper. So the main role of the chopper here is to break the steady light that is coming from the hollow cathode lamp into pulses. This helps the spectrometer to focus on the light that is absorbed by the sample and separate it from stray light, like for example, any light that is coming from the burner or any light that is coming from the flame. We need to cut that out and measure only light coming out from that is emitted, the light that has been absorbed by the sample. So the chopper does this role. Then the next thing is we have a flame or the burner. So the flame can be either, acetylene flame, or there are advances where a graphite also has been used. So we'll come to the advantages of using different flame sources, ionization sources in AS in a couple of minutes. So before that, then there is a monochromator. What the monochromator does is it isolates the required wavelength that is coming out from the flame and helps it direct it into the detector. There are different kinds of detectors that are used in AS. We have a CCD detector, then we can also have a CC charge coupled detector, charge ionization detector, and so on. The most commonly used detector is the CCD or the PMT detector, which converts the light into an electronic signal, and therefore the intensity of that light can be easily measured. Okay. Now, which of the two AS equipments are more suitable? What are the pluses and minuses of using one equipment over the other, or one model over the other? So here is a comparison of the two. If we are using flame AS, the sample here can be introduced as a solution, which gets then atomized into a flame which is at a very high temperature of around 3000 degree Kelvin. This flame can be made up of either an acetylene or a nitrous oxide. Okay. Flame AS disadvantage is that it has lower sensitivity as compared to the graphite. However, sample requirement here is in ml. Okay, 2 to 5 ml is usually required. This technique is more robust. Analysis happens faster. It has less matrix interferences, and it also is suitable for determination of elements which are present in higher concentrations. As opposed to graphite AS, here we do not have any acetylene flame. An electrically heated graphite tube is used. As a result, atomization can be done in a stepwise manner. Hence, it is more efficient. So the sample will undergo atomization in a stepwise manner. So it will strip off all the solvent molecules first, and then more energy will be provided to the atoms of the sample, which will undergo excitation. So the efficiency of atomization in graphite furnace is much higher. Therefore, sensitivity also is much higher. The sample requirement is lower. It is usually in microliters. Precision, unfortunately, now because it suffers from slightly higher matrix effects, the precision is slightly lower as compared to flame. But it is suitable for trace analysis, perform elemental analysis in trace quantities. So overall, atomic absorption spectroscopy, is highly specific because we are analyzing one element at a time. It is one of the most specific equipments available for elemental analysis out there. It has good sensitivity, wide linear range, low detection limits. It is relatively simple to operate. It's cost effective in comparison to the other more sophisticated equipments like ICP-OES or MPAS. And it is a very well-established technique. So if we consider it from regulatory aspects, it is definitely a technique which has been accepted worldwide by all regulatory agencies. The only limitation here is it is slow. So because we are measuring elements one step at a time, the duration of the analysis is longer. It suffers from matrix effects because of the low efficiency levels. It has a limited dynamic range. It does have certain operational issues in the sense that we have to change the source each time we want to analyze different element. Regular maintenance is required, and gas supplies are heavily used. The next spectroscopic equipment that we'll discuss is OES, or atomic emission spectrometry. So it can be ICP-OES or it can be MP-AES both. In all of atomic emission spectroscopic equipments, the working principle remains the same. So what happens here basically is atoms are excited. So the samples receive energy. As a result, these electrons in the sample are promoted to the higher energy state. This is called as the excitation. As I mentioned to you earlier, there are multiple excitation levels possible. Okay. After which, these excited electrons, now because electrons, when they move to higher excited state, they become unstable. They try and come back to their original ground state. This process is called as decay. So while coming down from the excited state to the ground state, they give out or emit electromagnetic radiation. And this electromagnetic radiation is captured by an optical system. This optical system that can be used here in ICP OES depends. So the detectors can be different. In certain cases, it will be a mass. So it will be categorized as an ICP MS equipment. In other cases, it could be a CCD or CID detector, like in case of ICP OES. So depending upon the excitation category, these equipments can be broadly classified into ICP or MP, that is inductively coupled plasma or microwave plasma. So the key components of an AES are, we have sample introduction unit, an excitation source unit, and an optical system unit. So the sample introduction system helps to transport our sample solution into the excitation source, where the excitation of the sample happens, uh, and the decay or the emission will be then captured by the optical system. So the sample introduction system is made up of a nebulizer, a spray chamber, a sample transport assembly, aerosol, and flow controller. So the main use of all of this is, so the nebulizer will help to transport the sample solution to the spray chamber or to the to the spray chamber. So the nebulizer, what it does is it will help to break down the solution into very fine particles, and which will be then captured by a spray chamber. The spray chamber will then filter out all these tiny particles. It will remove any large droplets from the aerosol, and it will also smooth out any fluctuations in the gas flows. Ultimately, the solution is then transported to the excitation source. So in the excitation source, depending upon the excitation source, as I told you, the equipments can be categorized into separate classifications, like an ICP. If a inductively coupled plasma is used, it will be ICP OES. If it is a microwave plasma, it will be MP AES, or an arc spark can also be used. So there are different equipments that are known according to the excitation source that have been used. So we'll see each one of them a little more in depth. Coming to inductively coupled plasma optical emission spectrometry, which is very popularly known as ICP OES, one of the most popular, one of the most sensitive equipments for doing elemental analysis. So the principle remains the same here. Only the instrumentation is going to change. So in ICP OES, the most key factor that drives the entire efficiency of this equipment is the plasma. Okay, inductively coupled plasma. Now, what is plasma? So if we see the diagram of an ICP torch, the blue lines here are the magnetic fields, and the arrows indicate the direction of the flow. So an alternating current will cause these magnetic field lines to continuously change direction. So in an inductively coupled plasma torch, usually a gas like argon flow is introduced, which then flows through this alternating magnetic field. The gas flowing through this region is made up of conductive material, and this conduction is provided with the help of these coils, induction coils, Tesla coils they are known as. The oscillating magnetic fields will generate electric current in the conducting argon, and because of its natural resistance, the oscillating magnetic field will then break down the chemical or the sample solution and cause excitation in the plasma. So the temperatures that the plasma can generate is up to 5,000 to 6,000 5,000 degree Kelvin. So the temperatures do vary depending upon the region of the plasma, but they can go up to as high as 5,000 to 6,000 degree Kelvin. So in an ICP OES equipment, the flame sources that if a flame source is considered, it has better atomization efficiency. So an ICP source will have better atomization efficiency, lower chemical interference, better sensitivity, and it also gives more stable signal. On the other hand, if a microwave plasma is considered, it has more matrix tolerance, but lower detection limits. Whereas in the arc spark method, it has less matrix effect, it has better reproducibility, better quantification, less sample preparation time, but at the same time, it has lesser sensitivity than flame sources. So after ICP OES, we come to the next important technique that I would like to discuss here is the MPAES. Microwave plasma atomic emission spectroscopy. Okay, here the microwave, instead of inductively coupled plasma, a microwave plasma is used. So the microwave plasma is here the excitation, the principle will remain the same. Here the nitrogen fueled microwave plasma reaches temperature around 5,000 degree Kelvin. At these temperatures, the atomic emission is very strong, and hence it produces excellent detection limits and a linear dynamic range for almost all the elements. So MPAES, okay, is a very environmentally compatible equipment where the magneton, industrial magnetron is used to form plasma from the nitrogen which has been extracted from compressed air. So there is a nitrogen generator that is connected to the equipment, which extracts nitrogen from the air, and this nitrogen then is used for running the MPAES. So in fact, MPAES almost runs on air. So using a magnetic field rather than the electric one for excitation generation, a very robust plasma is created, which is capable of handling a wide range of sample types. An optimized microwave waveguide creates concentrated electromagnetic fields at the torch. Then an axial magnetic field and radial electric field will contain the microwave energy to create a plasma. The process is quite simple. Similar to ICP OES, we have a sample introduction unit wherein the sample in the form of an aerosol is introduced into the flame. So this aerosol is created with the help of, initially we have a peristaltic pump which will withdraw the liquid from the sample tube. So even before we start the system, the sample equipment as whole, there are certain sample preparation steps that need to be carried out. So if the sample is in solid form, it needs to be microwave digested. The microwave digested sample needs to be converted into a solution, and only solutions can be introduced into ICP-OES or MPAES equipments. So once the sample has been digested and converted into a solution, it is poured into suitable vials, and these vials are then loaded onto an autosampler. From there, a peristaltic pump will transport that solution into a nebulizer. The nebulizer will then convert the sample solution into fine droplets and pass it to a spray chamber. As already mentioned earlier, the role of the spray chamber is to filter out fine particles and remove any excess or large droplets from this aerosol so that only fine particles reach the flame. Now, what the main reason why this is done is because as soon as the particles, fine droplets reach the plasma, firstly, they should not change the temperature of the plasma. The large molecules, so it will take time. If the droplet size is very large, it will take time for the entire excitation process to occur, because it has to undergo evaporation, and then it will then gain energy. So the steps, instantaneous excitation will not take place. So it is very important that very fine particles are introduced into the plasma. So this is, the plasma will then convert it, or rather ionize the sample, and the particles will then emit a particular wavelength, which will be captured, filtered out using different lenses or monochromators, and detected using a CCD or an CID detector. So the optical system, main role of the optical system is to direct any incoming radiation to the detector. The detector will then capture the signal, and it will give us a report which will correlate the intensity, the wavelength and intensity of the emitted light to the element that might be present in the sample. So this will give us qualitative data. Quantitative data is usually generated by introducing a solution, a standard solution of known concentration, and subjecting to all the steps that the sample is also following. Next, coming to ICP-MS. So when the detector in an ICP system is mass spectrometry, it is called as inductively coupled plasma mass spectrometry. One of the, so here also almost all the initial or equipment related parts will remain the same, except that the detector can be either a quadrupole, a time of flight, or a magnetic sector detector, like a, you know, it could be a multiple capture detector and so on. So major advantage of an ICP-MS equipment is, which no other technique has, is that it can measure isotope ratios. Yeah, this is one of the key factors why ICP-MS is preferred for certain applications and does not have an alternative. So there are other equipments that also do the job, like an IRMS, okay, isotope ratio mass spectrometers. But MPAES or ICP-OES or AS or X-ray or CHNS analyzers cannot measure isotopes. So depending upon the type of detector that is used, ICP-MS equipments are then categorized or known popularly as quadrupole equipments or TOF equipments or MS equipments. So quadrupole is one of the most popularly used detectors. It works by using oscillating electric fields to separate ions. It is very useful for routine analysis. It offers mass resolution of a single unit. It is less expensive in comparison to the other two and has a very fast scanning capabilities. Whereas in time of flight, it separates the ions based upon their flight time. It is excellent for rapid multi-element analysis, can detect almost all masses simultaneously. Okay? And it is good for transient signals and moderate resolution. Magnetic sector has the highest resolution of all available equipment. It uses, so the working principle here is it uses both electrostatic as well as magnetic fields. Okay, it has great abundance sensitivity, better precision, as well as isotope ratio measurements, but is much more expensive and has very slow scanning rates. Okay. these were some of the spectroscopic equipments are some of the most popularly used elemental analysis techniques out there. However, uh, we are seeing a lot of um, you know usability as well as interest that is being generated for using X-ray techniques to perform elemental analysis. It is, of course, it's a very old technique. It is time and trusted technique. It has been regulatory approved, but it has also certain limitations in terms of the range as well as in terms of sensitivity that it offers. However, for certain applications, X-ray technique are very popularly used. So when I say X-ray techniques, it includes both XRF as well as XRD. Okay. The principle of an X-ray technique is again very similar to what a spectroscopic equipment can is operated on. Only difference is that instead of using a plasma or instead of using a flame, an X-ray, okay, is used here to excite the molecules. So the sample preparation steps remain the same. So there is, an in an XRF technique, it will directly measure concentration of elements in a sample by detecting the characteristic X-ray emissions, that are emitted after a particular electron has been ejected from its ground state to its higher orbital state. Right. So the prepared sample. So we have a sample which usually is so the advantage of an X-ray technique is solid samples can be directly introduced. So there is it is not necessary that the samples need to be converted into a solution form. So the sample is placed in an XRF analyzer, which emits very high energy X-rays towards the sample. This high energy X-rays strike atoms in the sample and cause the inertial electrons to be ejected. As soon as this happens, there are vacancies created. So the electrons from higher energy levels can fill up. So electrons from this higher energy levels will then fill up these vacancies. And during this process, okay, they emit secondary X-rays. These X-rays are very characteristic to the specific elements and which can give us insights into elemental composition of that sample. So there are two techniques that are commonly used. We have an XRF machine and we have an XRD machine. So XRF is specifically designed for elemental analysis. It directly measures concentration of elements in a sample by detecting the characteristic X-ray emissions. Okay, so it can be it is usually used for elements above sodium in the periodic table. Right from sodium to uranium, all elements can be determined. It provides quantitative results, can analyze samples non-destructively. So this is very important. We can reuse the sample for other techniques. It can work on all types of matrices, so solids, liquids, and even powder form. And it requires almost no sample preparation. So while X-ray fluorescence has so many advantages, in comparison, XRD is primarily used to determine structure. No, it is not a technique of choice for doing qualitative or quantitative identification as well as estimation of elements in a sample. It is more of use when we want to identify how a particular element has been arranged structurally within that sample. So XRD will give us indirect information about the elemental composition based upon the crystal structure. Okay. So this is not usually always the primary function that a particular analyst is looking for. Hence, XRD machines are not that popularly categorized under an elemental routine or popular elemental analysis technique. Then coming to a CHNS analyzer, as the name suggests, a CHNS analyzer will determine carbon, hydrogen, nitrogen, and sulfur present in the sample. So these four are usually substances which are not measured routinely using any other technique. Like for a ICP-OES or an MPAES, usually we do not measure CHNS. Because CHNS analyzers fulfill that particular requirement, as well as they have a specific methodology where accuracy, precision, detectability, range, everything has been taken care of. So CHNS analyzer are primarily used for organic compound characterizations. They help. What information do they give? They help us to determine empirical formulas, or they give us structural information or structural conformation. Sometimes they're used also for doing purity assessment of a particular sample. So here it's very simple. So the sample is usually combusted. So it undergoes complete combustion at high temperatures, at temperatures of around 1000 degrees Celsius. And they are then converted into their gaseous form. So carbon will be converted to CO2, hydrogen H2, nitrogen into N2, and sulfur SO2. This gas is then directed into a GC equipment, okay, which has all the GC columns, TCD detectors, and other parts, which will help detect which gas is coming out. So this is how a CHNS analyzer works. So if we want to determine uh, the organic elemental composition of a particular sample in a very fast way, this technique is very useful. It has good accuracy, precision. Sample requirements is not much. A few milligram of sample is enough. It can simultaneously measure uh, all of the three CHNS with very minimal sample preparation. However, because it works on the principle of combustion, it is a destructive technique. It cannot analyze inorganic materials. Sample must be completely combustible. And so it is limited to CHNS. So if this is not uh, a technique which will offer a wide range of applications. So now that we've seen all the popular elemental analysis techniques, now I've put here a slide which will compare all these techniques depending on different parameters and application ranges that it has to offer. So AS equipment has very high sensitivity for certain elements, especially metals. ICP OES has moderate to high sensitivity for a much wider range of elements. MPAES has lower sensitivity as compared to ICP OES. MS has the highest sensitivity, and XRF will also have moderate to high sensitivity, but limitation is that it cannot monitor very light elements. So the detection limits, AS works in nanogram to picogram levels. ICP OES can measure from ppm to ppb levels. MPAS works from ppm to ppb levels. ICP-MS can go up to ppt levels. X-ray also works in the ppm to ppb. So it again depends upon the metrics. It has pretty good detection limits. Speed. AS, if we consider one element at a time, AS is pretty fast. So if the only bottleneck is if we want to do multi-element analysis, AS suffers in this category. But for if we are comparing elemental analysis of only a single element, AS is very fast. Time required is typically less than 1 minute. ICP-OES, on the other hand, will require slightly more time. MPAS, moderate. ICP-MS requires slightly longer times in comparison to the other two, because it will also involve a lot of sample preparation, and we have to get rid of matrix completely in order to get good detection limits and precision. X-ray is one of the fastest. So AS in terms of high throughput is fairly good. ICP OES has the capability of doing multi-element analysis. So does MPAES. ICP-MS, because the scanning rates are slightly lower, the detector scanning rates are lower, the speed and throughput capacity definitely is lower than the other two. And XRF has very high throughput analysis because no sample prep is required, and no, detection limits are fairly good. When it comes to sample preparation, AS for all the three, rather for AAS, ICP, OES, MP, AES, and ICP-MS, we require to convert the sample into a solution form. So sample preparation is required. The only difference is that ICP, OES, and MP, AES can tolerate a little bit of more solid concentration. So the TDS tolerance of ICP-OES, AAS, ICP-OES, and MPAES is slightly higher as compared to ICP-MS. In ICP-MS, the solution has to be stripped off of all the matrix components. In XRF, there is no sample preparation required, as we can measure solids and powders as well. In terms of cost, AS is relatively low. The cost of the equipment is low. The highest equipment cost would be that of an ICP-MS. ICP-OES and MPAS fare almost same if we are considering only the equipment or capex cost, but operation cost, MPAS, because only a nitrogen generator is enough. The operating cost of MPAS is much lower. X-ray is expensive, especially the advanced equipments, and the range can be really varied. So limitations. Certain, it is limited. AS is limited to certain elements, uh, and so are other techniques. But complex matrix interference is one of the problems here. Matrix also is a problem when it comes to ICP OES. Some MPAS, fortunately, matrix tolerance is much higher. ICP-MS, one of the key bottlenecks is that it requires a highly skilled operator, a lot of training to operate it, and it suffers from a lot of interference, not only from the matrix, but from isotopes of the other elements as well. XRF, it has lower sensitivity for lighter elements, and it is limited to surface or near surface analysis only. Okay, it cannot do in-depth. If you want to measure like a biological sample of a few thickness of a few millimeters, element concentration of or element analysis of the deeper layers cannot be performed. So how to choose the techniques from all the available techniques that we saw here? What should be our considerations in order to select a technique for a particular sample or application? First, each technique has its own strengths and weaknesses. So we need to start first to understand whether what is the sample state. Is it a solid or a liquid or a gas? So if it is a solid, we have to convert it into a liquid form. If that seems troublesome, then and if that is out of question, then for determination of solid, XRF is the only technique available. If it is a gas, and if you, again, it depends upon which element you want to analyze. So if I want to analyze, elements like only carbon or hydrogen or nitrogen, CHNS is the technique of choice. If I want to analyze isotopes, then ICP-MS is the technique of choice. If I would like to analyze very trace quantities of certain heavy metals like mercury, in very low concentrations, then ICP-OES is the technique of choice. So it also depends on what is the sample volume that you are targeting for the analysis per day. So if the throughput required is very high, then um, it is essential that you use a technique which will do a very fast scanning, like in case of an ICP OES equipment, or ICP no ICP OES or MPAS will give you sample throughput which is in a few minutes, whereas ICP-MS will require much longer times, and AS will require longer time if you want to analyze multiple elements. If the target or if the objective is to do a single element, like only lead determination in 2000 samples, then AAS will work fine because it does scanning really fast. It gives high throughput data, but it will measure only lead. We cannot simultaneously measure mercury. What is the lowest analytical concentration range that is necessary? So yeah, the detection limits is something which probably is one of the most crucial factors while deciding the choice of equipment that you want to go to. Lowest detection limits are possible with ICP OES and ICP-MS. So they are even better than XRF. So PPT levels are possible with ICP-MS. We have seen that PPM levels will be possible with AS, but not always trace element analysis is required. Sometimes, let's say, for example, for identification or purity assessment of multivitamin and multimineral tablets, where concentration of these minerals is really high. In those cases, when concentration of a particular element is very high, AS would be the technique of choice because it has a very wide linear range. Okay, so now keeping this in mind, the regulatory bodies all across globally, have classified elements in different categories, and because of the challenges that the consumer is facing from contamination of certain heavy metals in foodstuff or contamination of heavy metals in the environment, and all of this, guidelines keep on revising. So ICH Q3 guidelines has been specifically prepared, keeping in mind the necessary workflows that need to be incorporated while doing elemental analysis of certain categories, like for class 1, which are we call them the heavy 4, which is the heavy metals like arsenic, mercury, lead, and cadmium. Yeah, these are the most toxic. Class 2A are less toxic. It depends on the probability of occurrence. Class 2B are toxicants which have reduced probability of occurrence, and class 3 are relatively less toxic but might require assessment depending upon what is the dosage form. Coming to applications of elemental analysis, we'll just quickly go through it. This is a very wide topic. Applications range right from petrochemical for determination of certain volatile organic compounds to heavy metal analysis, yeah, to food and agricultural sector, where determination of heavy metals is very, very important and binding by regulatory bodies. So determination of cadmium, lead, certain analysis of nutritional content in soils, or multi-element analysis in feed. All this can be performed. For environmental and geological applications, so from drinking water to fly ash, coal determinations, elemental composition in purity assessment, of certain geological samples. For carbon dating, ICP can be used to determine the age of a particular meteorite, for example, and so on. In chemistry, of course, for material science, this is extremely essential in an R&D lab. So to determine concentration of different elements in cement, ceramics, glass, polymers, plant extracts, or tissues, biological fluids. So R&D labs require estimation of trace as well as uh, major elements routinely. So with this, we finish off the theoretical part of it. I would like to take few moments here to mention that at Venture Center, we have a dedicated facility which offers elemental analysis using MPAES. Now we have a trained staff which does end-to-end service delivery. So you can submit a wide variety of samples here. We have the capability and expertise available to convert your sample, be it a solid or a liquid or untreated sample completely. So that can be microwave digester, and then it will be analyzed using an MPAES equipment. Um, we also have a wide application range possible. So right from heavy metals to trace metal analysis, we are equipped to do everything here. Right. So our delivery times are very low. So we target our turnaround times to around 4 to 5 days. So once the sample has been received within maximum within 3 to 4 days, you should be getting the results. So this is what we take pride in. And with this, I end the session and would like you all to. So if you have any questions, I would really like to open this session for getting this more interactive.
Yes, I think Jignesh has a question. Yeah, Jignesh, you may unmute and please go ahead and ask your question.
Sure, ma'am. Yeah, it was a very informative session, ma'am. I just had a question regarding the C. I have a particular requirement for carbon nitrogen ratio in compost. So we are preparing compost from agriculture waste, from agriculture residue.
Okay.
And in that compost, so at day 0, when we start, the starting material is there. From there to a month or two, after a month or two of this process, what is the change in the carbon to nitrogen ratio? That is what I would like to determine. So,
okay.
Which technique should
the CHNS technique will be most applicable for this particular request.
But then in the compost mixture, there will be some soil as well, like the process. Apart from
it doesn't
the
matter. It doesn't matter. So the CHNS, because it is the sample is going to undergo complete combustion. Any other all the other remaining things aspects will be taken care of by the equipment. So it is a very popularly used application, for soil analysis. CHNS can definitely help you with there.
Charges for a sample.
Hello, can you please repeat?
What are the typical charges for analysis of one sample?
No, unfortunately, at Venture Center, we do not have facility for CHNS.
Oh, okay. Right.
But just as a follow-on, Mr. Jignesh, what you can do is you can write us an email, and if the CHNS analyzer is available in the neighboring facilities of ISOR or NCL, we'll be happy to connect you. However, at Venture Center, as these last slides mentioned, we only have MPAS system. CHNS analyzer is currently not available. So you can always drop us an email, and if it's available at ISA, we will connect you to the concerned person. You may reach out separately to them.
All right. Thanks. Thanks a lot.
I think Mr. Nitin Kadam also had raised his hand. Mr. Nitin, do you have a question here?
Hello. Yes, ma'am.
Yes,
Yes,
Nitin.
hello.
Yes.
We have Agilent 780 ICPMS system, but we don't have micro digestion system currently in Pune University. So can we hire your micro digestion system there for the sample preparation purpose?
Yes, I think that is possible. You want to only avail the microwave digestion facility,
Yeah. So
right?
most of the users from college and all, they don't have digestion facility and all. So
Right.
they were not. That's why they are not directly give the sample to our center. So if your micro digestion system, if load is not there so much, so on the queue basis, that can be hired, and user can get at least digestion facility, and they can avail
Yes.
benefit of your lab also, and as per the queue in our lab also.
Yes. So you will have to submit the samples. We cannot allow you to come here and operate the equipment. So you can write a mail to us. We'll provide a particular slot on which during that time you can come and submit the sample. We'll do the digestion and hand over the sample to you.
Yeah. Okay. Thank you. And nice session.
So
Thank you for
thank you.
elaborate. Yeah.
Yeah. Any more questions?
I think Prajakta. Yes, Prajakta.
Yeah. Hello, Deepti. It was very nice session. I just wanted to ask whether the other side of the elements, like non-metallic elements, that won't be covered under our facility, like
Uh,
fluoride, chlorides.
no. So halogens cannot be measured. So halogens cannot be measured using MPAES.
Hmm.
So all the halogenated compounds, are not basically possible using our facility.
Our facility. So,
Yeah.
for lower detection, lower sensitive detection of these elements, ion chromatography would do more performance.
Which element are you talking about specifically?
Fluoride.
Fluorides. So
Yeah.
fluorides, hmm, actually depends upon what is the matrix that we are looking at. If it
Okay.
is if it is a sample, if it is in a solution form, so are we looking at like a soil sample, or are we looking at a biological sample? From
Biomass,
there,
we are looking.
biomass. Okay.
Hmm.
So fluoride concentration, I think I'm not sure, but probably ion chromatography should work. But
Or classical methods only we should follow.
classical methods would also give good enough results. But I think if we are talking about instrumental sections, I think XRF will also give
Okay. Okay.
some,
XRF also.
yeah, should be able to
But
give some
particle
data.
size limitation is there.
What limitation?
Particle size of the sample, is it
No, I don't. No, no, no. So it will usually it will it does not have a limitation on particle size. It has limitation
okay.
on depth. So it
Okay.
usually does super like surface topographic measurements,
Okay, fine.
or it will go up to a particular depth only. So it cannot give you accurate data for a very thick sample.
Okay, okay, fine. Thank you. Yeah, that's it.
Sure, thank you. So for all the participants who are here, I'd also like to, say that in continuation to this session on 6th December, we are organizing a consultation clinic where, you all can ask any specific queries related to elemental analysis to our experts, and you will get a 30-minute session, for a one-on-one discussion with our experts. Details I will be sending over email. As we now, come to the end of the session, firstly, I would like to thank our speaker, Dr. Deepti, for taking all the efforts and putting together a great presentation. Thank you, Deepti, very much for your efforts. I believe all the participants will agree with me that in the little time that we had, you managed to touch base with all the popular techniques, and even you managed to highlight all the critical aspects. So thank you very much for that. And yeah, thank you for all the participants and VCT members who have attended this session. And I'll be sharing a feedback link over email with all of you. Kindly share your feedback with us so that we can, for the upcoming sessions, we can improvise. Thank you very much, and I'll be now wrapping up the session here. Thank you, everyone.
Yeah, thank you, Edna. Thank you for giving me this opportunity, and I hope it has benefited our participants as well. And do check out our websites and our social media handles to get updates on more such sessions in the future.
Sure. Thank you. Thank you.
Thank you.